Good morning, everyone. Thank you. This is a great turnout. I'm so happy that everybody made it today. This is Professor Matthew Weisenberger, University of Kentucky. And Professor Weisenberger was selected as the 2023-2024 Graffin Lectureship Award winner by the American Carbon Society. The Graffin Award is sponsored by Asbury Carbons, of course. Matt is going to talk a little bit more about the Graffin Award in his presentation, so I won't talk any more about that, but I will read this with my two pair of glasses. Okay, so Professor Weisenberger earned his BS from chemistry at Georgetown College and was awarded a Master's of Science and a PhD in Material Science and Engineering from the University of Kentucky. He's currently an Adjunct Assistant Professor in Material Science and Engineering at UK and is a member of the graduate faculty. Dr. Weisenberger has been at the University Center for Applied Research since 2000, and since 2015 has served as Associate Director and leader of the Carbon Materials Group. Since the early 2000s, a large part of Professor Matt's research is focused on carbon fiber processing, structure, and performance. Dr. Weisenberger served as a member on the Executive Committee of the American Carbon Society and is currently a member of the Advisory Committee of the American Carbon Society. Please join me in welcoming Matt Weisenberger. Thanks so much.
Thanks again, Albert, and thanks to all of you for showing up today. It's really special to be here at Asbury Carbons to present this Graffin lecture, which has been so long sponsored by Asbury Carbons. So today, I'm going to talk about the history and the present and the future of carbon fiber. And then we can take questions on some other things as well. But I hope that I can take you guys a little bit along on a historical journey of carbon fiber for about the first half of the talk. And then I'm going to kind of just rehash where we are with carbon fiber. And then I'm going to talk about where we might go in the future with carbon fiber and what we're doing in my research group. So as Albert mentioned, the Graffin Lectureship dates back to 1978 and, sponsored by you guys. It is each year the American Carbon Society selects a new lecturer, and I was the 23-24 lecturer. And the goal is largely to promote interest in carbon and graphite science. And I was actually at City College, New York yesterday, so happy to have this workout record come here today. It is, of course, sponsored by Asbury, and, here we are. Don't need to go through this with you guys, but I did this with everybody else, so they.
Good job. Good job.
Also, it is named after George Graffin.
Yeah.
And I, of course, never met George, but Albert told me about George. Was a recognized leader in the natural graphite industry. So there's his
The appropriate name
photograph.
for it.
Yeah. Good deal. And this, again, going back to 1978, I'm really humbled to be on this list. There are some really big names in carbon science on the list. I've highlighted a couple. The first over there, Leonard Singer in 1983, along with Lewis in 1986. These guys were really pioneering the mesophase pitch-based carbon fibers out of Union Carbide. And then Roger Bacon, largely regarded as the founding father of structural carbon fiber, also out of Union Carbide, gave the presentation in 1989. Also, Teresa Bandos from City College, New York is on here too, and I pointed that out to her again yesterday. All right, so I thought I would just kick off just to describe some of the applications. I'm sure many of you are very familiar with all these, but it gets us moving down the path in this area. Obviously, commercial aerospace is probably the largest synonymous area of carbon fiber. It is probably the single largest demand side for carbon fiber for passenger aircraft. Obviously, you want really lightweight, strong materials for aircraft. Boeing picked up on this in the early 2000s and produced then their 787 using something on the order of 50% weight carbon fiber composites to essentially enable a big jump in fuel economy. And that's a big deal for an aircraft that has a service life of 40 to 50 years and is flying on average something about 11 hours a day. It's a lot of fuel. But the same physics apply to other things, and I'll get to that. Another area that carbon fiber composites are really growing in is wind energy. So here, you guys have seen these windmills, and they're made, usually with 3 large wind blades. And those blades, as they get longer, they circumscribe a larger circle. That's directly proportional to the amount of power that they can generate. Also, as those blades go higher in the air, they can generate more power. But as you know, if you generate a longer blade, you're going to need to stiffen it or it's going to flop around potentially. That's bad news. So they incorporate what they call a spar cap, which is basically an I-beam of sorts made out of carbon fiber that goes on the inside of these rather large windmill blades. Good. Except no substitute. If you're going to go for a supercar, they're all going to have lots and lots of carbon fiber in them. I just pointed this one out of Sweden because it's the fastest, I think, production car you could possibly get. I think it's going to cost you a cool couple $1 million, but it's largely modeled after an F1 car using carbon fiber and everything. And the idea is, of course, to make the vehicle extremely lightweight. These things have power to weight ratios on the order of a helicopter. But in any case, even carbon fiber wheels these kind of cases. Now, really rare, right? But larger volume carbon fiber production cars have occurred. This is BMW SGL's joint venture into the production of their i3 vehicle. Now, no, that vehicle is no longer produced. I think they stopped production in 2018. And I'll touch on why I think that might have occurred. But the same physics applies. If you can lightweight vehicles, you can improve their essential fuel economy, or just the energy utilization of the vehicles. And same thing all the way down to bikes, right? So serious cyclists are looking at things like carbon fiber bikes and are willing to pay a pretty large price for those. This is an interesting application that I thought I would also highlight because it really capitalizes specifically on the high tensile properties of carbon fiber. Really, it's the high tensile per unit density of the carbon. Yesterday in New York City, really high-rise buildings, these elevator shafts containing multiple steel cables, the weight of the steel cable itself can far outweigh the car and the people and stuff in the car. And so as you go ever higher, the advantage of using a lightweight tensile cable, in this case, is pretty evident. So I thought it was an interesting application for using high tensile strength carbon fiber, right? And then in the world of science fiction is the elevator to space. But, folks have seriously studied this, and it is in principle possible, but in practicality not, because we don't have a material that can handle the amount of tensile stress. It effectively weighs too much to do. So this was made famous in Arthur C. Clarke's book, The Fountains of Paradise in 1979, but there were concepts of this going back into the 1950s. But it all comes down to the specific properties of the carbon fiber. And I want to define that. That has to say that's the strength of the material on the y-axis, the strength of the material per unit density of the material, in this case versus the modulus, or the, say, resistance to deformation under load of the material divided by its density. So if we look up in the upper right quadrant of this chart, we'll find the highest performing lightweight materials in tension that we know of. All of these in blue, the blue open circles, are carbon fibers derived from polyacrylonitrile. And we'll get to that and unpack that a little bit more. But these far outperform materials, for example, metals down here in the very low left corner, as you might expect, and then some other carbon fibers and glass fiber. It's interesting that the polyethylene fiber is performing so well here, but we can't forget that polyethylene doesn't like to be heated much, right? So, and the other thing is that polyethylene strains more, it actually stretches more. So these carbon fibers used to make composite over pressure vessels containing 10,000 psi hydrogen, for example, they have to contain that measure of load, but they don't need to like expand a lot either, and they have to resist temperature. And those kind of concepts go across all of those applications I talked about. Primary structure in aerospace, even to, for example, the hoisting cables for elevators. Okay, I want to now kind of dive back into history a little bit. And where did all this come from? How did we land on let's make fibers from carbon for purposes like for strength? Well, that story begins in the middle of the 1800s when folks were looking at trying to produce artificial light. And the one that comes up, of course, is the graphite arc lamp that was lighting the streets of London this time. You have two graphite elements or electrodes, and you run current through them, striking an arc between them. It's almost like a welder, right? So sort of this bright light that was lighting the streets, buzzing along, and it was all made possible by the carbon electrodes. At the same time, there was a lot of interest in getting to an incandescent light bulb. After all, this is sort of the height of the Industrial Revolution. Folks, of course, want to be able to light their homes, right? Because we're using candles and whale oil lamps, but really want to light the factory floors and keep production moving. And the incandescent was one of the things that folks were really trying to get at. Of note was the British inventor, Sir Joseph Swan, who really between 1850 and 1880 was doing all sorts of experiments to actually land on a functioning light bulb. And in so doing, he patented this in England and in the US as well, describing that he could produce a conductive element from carbonized cotton thread. And, other materials would essentially burn up or melt when you tried to run enough current through them to have them light up. So I found this to be an interesting historical point. Right around the same time, in fact, a couple of months earlier, although the exact who did what first is certainly controversial, but nonetheless, Edison patented in 1880 in the US the same effective outcome. Carbonized linen thread, cotton thread, wood splints, and so on and so forth. These are shown, you can't really see them, but in the light bulbs, these are like brittle filaments though. And they wouldn't really be a carbon fiber that we know of today that has any sort of supple character. But they survived the current and were able to incandesce. Later, not long later, Edison reported carbonized bamboo filament that got the up to 1,200 hours on a light bulb in the 1880s. This, although was all supplanted by the tungsten filament light bulb, came into existence around 1904, except for some really boutique applications of the carbon filaments on Navy ships. Now, when we think of carbon fiber, though, we don't really think of filaments and light bulbs, but there's a tie back to this. But the fibers that we think of are supple and strong and can kind of behave like a textile or a fabric. These, however, have the roots in the arcs and the light studies that were going on. We'll talk in a minute about cellulose fiber, pan fiber, and pitch fiber, but I want to kind of get on to now the first structural carbon fibers, which were about a century later, starting around 1959. Around this time, Roger Bacon began work at the Union Carbide Corporation in Parma, Ohio, and in the late 1950s was studying the triple point of carbon out here, which is the point at which the carbon, solid, liquid, and vapor, that's right, vaporized carbon, exist in equilibrium. So he was working at an incredibly high temperature, something on the order of 3,600 degrees C, achieved by doing arc discharge. So he was running current through graphite electrodes, striking an arc at extremely high temperatures, albeit very transient, but under extremely high pressure. And I think this was high pneumatic pressures of noble gases in this cell. And when he took the cells apart, he noticed over and over that on one of the electrodes, there had grown all these whiskers of graphite. And he described breaking up in one of those electrodes, and it looked like a Christmas tinsel of all these little whiskers of graphite. And he took those out and began to study those and found that he could take these little whiskers of graphite and kink them back and forth, and they would bounce back. And he was able to, in fact, test them in tension and found the tensile strengths of these of something around 20 gigapascal. Just to be clear, that's more than double the tensile strength of the best carbon fiber you can commercially lay your hands on these days. Also with a modulus of about 1 terapascal or 1,000 gigapascal. And this is consistent with loading graphite along the basal planes of like a perfect single crystal graphite. So these were essentially little perfect, almost perfect single crystal whiskers of graphite. But this sort of inspired a lot of interest in high strength carbon fiber. Prior to this, no one was really thinking of carbon or graphite being high strength, particularly in tension. After all, it was a lubricant. It was used for a lot of things that you guys know much more than I do, right? Some the metallurgical industry and so forth. But Union Carbide knew that they couldn't really scale up all these little whiskers of carbon. So what did they do? They looked back and remember, almost a century before, folks had been carbonizing cotton, cellulose, to make light bulbs. And at the same time, the DuPont company had established one of the first synthetic fibers, the rayon fiber, based on cellulose, started in 1924. So about 30 years later, Union Carbide began to study carbonizing fibers of cellulose for higher strength. And shouldn't be pointed out that cellulose has got a lot of oxygen in it. That's not good in the sense of you're interested in the carbon yield. Something like 20 to 30% of the weight of the cellulose was converted to carbon. It's kind of low. But nonetheless, they were successful in producing a carbon fiber that had pretty good strength for the day, so about 900 megapascals. And later that year, actually in the following year, 1964, Bacon and his colleagues patented what they called a hot stretching process. We had to take these cellulose fibers through these furnaces and actually stretched it while it was forming and produced a modulus in the fiber of 172 with a strength of 1.25 gigapascal. Low by today's standards, but in 1964, this was the first structural carbon fiber ever produced and marketed as Thornell 25 in 1964. And it went into NASA's Gemini program at the time. Oh, I should point out that for this and other things, the Union Carbide was awarded a National Historic Chemical Landmark. So up in Parma, they have this landmark for the development of high-performance carbon fiber. Now, about around 1950, DuPont was also sort of pioneering a synthetic wool substitute fiber, which they called Orlon, and it was based on polyacrylonitrile, which has the structure over here in the corner. So you have the acrylonitrile group out there. And Ray Hoots was a chemist there who described that he could see that the fiber would change color as it was heated, from white to yellow to brown to black, and that the black yarn was remarkably stable to further heating, even in a Bunsen burner flame. So this gave insight that this fiber too could be of great interest as a carbon fiber. In the same paper in 1950, he described also the chemical conversion of polyacrylonitrile to the stabilized intermediate, essentially. And folks were recognizing that something on the order of half of the mass could be converted to carbon. So in Japan, this was at the Government Industrial Research Institute in Osaka, Japan, in the late 50s as well. Akio Shindo got his hands on a Scientific American magazine that reported the polyacrylonitrile fiber. I'm sorry, it reported the cellulose fiber carbon. And he got a sample of DuPont's Orlon fiber and began to carbonize that in his labs in Japan. And what he did at first was he took a really tiny amount of the pan fiber and put it in his furnace and converted this to carbon and observed that out of the furnace came a very nice supple fiber that he could wrap around his fingers and pull. However, when he repeated the experiment with a lot more of the fiber, what came out was very, very brittle. And this gave us, for the first time, insight into the role of oxygen on the very front end heating process. In the latter case, he consumed all the oxygen and didn't arrive at a nice oxidized intermediate, and the resultant carbon fibers were quite brittle. So this was a big leap in pan-based carbon fiber that was occurring right at the end of the 1950s. In 1964, Toray, the big Japanese fiber manufacturer, got quite interested in this and effectively commercialized the pan-based carbon fiber, which hit the market in 1971. They did a lot of work in comonomers for stabilization around that time as well, but they were really first on the scene for the pan-based carbon fiber. In England, at the late 60s, at the Royal Aircraft Establishment in Farnborough, Dr. Watt, William Watt, and his team were also really interested in carbon fiber. After all, they had come from the World War II era. They were trying to stay on the cutting edge of aviation. And they knew that having these really high strength, lightweight fibers were going to be enabling for new generations of aerospace materials. And his crew is credited with applying tension during the stabilization of these pan fibers. So they're tension these, much like Bacon did in the conversion of the cellulose fibers. In fact, in his patent, it describes the necessity to restrict length change or even stretch the fibers during the oxidation process. And in England, the fiber manufacturer there was Courtaulds, sort of the DuPont of England, and they were producing acrylic fiber, and they also teamed up with the Royal Aircraft Establishment and Rolls-Royce to essentially commercialize and scale up pan-based carbon fiber in England. Back in Japan, in the mid-60s, Otani and his group reported for the first time then making carbon fibers from pitch. Now, I think you guys probably know a little bit more about what pitch is. A lot of folks have no idea, but briefly, it is, unlike a polymer, it is comprised of small molecules. In this case, these polycyclic aromatic molecules over here on the right. And Otani showed that he could spin these into fibers and he could convert those into carbon. And the yields were really high. Something up 50 to 80% of the mass of those fibers will be converted to carbon. So Union Carbide kind of latched onto these results as well and doubled back efforts to try to produce carbon fibers from what they call the mesophase pitch. And Lewis and Singer also Graffin lecturers that I pointed out, they were highly involved in the development of the mesophase pitch-based carbon fiber. These are fibers that create a really high degree of graphitization, and I'll talk about some of the pros and cons of those. But today, there are only three companies in the world producing mesophase pitch-based carbon fibers. Two of those in Japan, and one still the remnant of Union Carbide operating in Greenville, South Carolina. Now, the advantages of the mesophase pitch-based carbon fiber is that it's melt spun and it's fairly low cost. Pan-based fiber has to be spun from solution and pretty much the cellulose fiber as well. Melting and spinning is just far simpler. That's good. Also, no tensioning is needed during the thermal conversions of those fibers. So that's good. Extremely high yield. 80% of the mass converts to carbon. That's good. Really high modulus fibers are capable. You can see in red here. These really high pitch-based carbon fiber moduli can be accessed. And kind of along those lines, high thermal conductivity of those fibers. But disadvantages with respect to PAN is these fibers are far more brittle, far lower strain to failure, low compressive strength, and they have a high price. I don't think that's the same as saying they're high cost. There's I think, a pretty large margin in the pitch-based carbon fibers. But these disadvantages, particularly the low strain to failure and the brittle, is really the issue. And the PAN-based fibers offer a higher, tougher fiber that's more stretchy, and toughness wins at the end of the day for a lot of these composites. After all, you don't want to build primary aircraft structure that's brittle. You want it to be light and strong and not to deform a lot, but you don't want it to crack like like an egg. So that means after 50 years since the 1971, the PAN-based carbon fiber, I would say, still reigns supreme by far. That's something like 90% of the market is PAN-based carbon fiber, and I think generously 10% is pitch-based. And as I mentioned, all this stemming from the high toughness of the PAN-based carbon fibers for the primary aerospace, which has really propelled it in the recent decades. Just as a recap on the PAN-based carbon fibers, in Japan, starting in the early 1960s, and then over into the early 70s, Toray by then had established themselves as the first production of PAN-based carbon fiber. In the US, all of the earliest work was with Union Carbide, which eventually, actually did a joint technology agreement with Toray at that time in the early 70s. That company essentially became Amoco, then BP Amoco, and Amoco Performance Products. I'm not sure on the exact chronology of that. Then became Solvay, Cytec Group, should say Cytec Group, then Solvay, and now is Syensco at Greenville, South Carolina. In England, the group with Courtaulds and the Royal Aircraft Establishment started with help from Rolls-Royce. Those precursors were used in the first Hercules fibers, which were carbon fibers produced in Delaware, which became the Hexcel Corporation, which still operates today, making fibers in Alabama and in Utah. But the bottom line is that if we want to focus on the strength of the carbon fiber, that has evolved over these 50 years, kind of slowly. I mean, apart from this group of points here right in the late 80s, mid-late 80s, this strength kind of marches up pretty linearly over the course of 50 years, starting at around 2.5 gigapascal. And last year, about 1 year ago exactly, Toray introduced the T1200 at an 8 gigapascal strength. All this kind of starting back in 1964 with Union Carbide's Thornell 25 at 1.25 gigapascal strength. But let's not forget that this was all kicked off by Bacon's graphitic whiskers at 20 gigapascal strength in 1959. So we still have room to advance the carbon fiber, but still reaching a tensile strength of 8 gigapascal is pretty remarkable. And it's really limited by the defects on those fibers. So you can kind of see in this SEM picture there. Yeah, sorry about that. You can see in this SEM picture that there's sort of a point here and a sort of chevron pattern that is radiating out of that fiber. All of these fibers in tension fail from some defect that's present on the surface, or perhaps some void or inclusion that's interior to the filament, but particularly on the surface. And this paper out of Georgia Tech described this pretty interestingly, plotting the tensile strengths of the filament versus the critical defect size on the filament. So if we take, for example, a fiber that has an average of a 6 gigapascal tensile strength, that will map to a critical defect of on the order of 20 nanometers, which is remarkable if you think about that. That means thousands of tons of these carbon fibers being produced cannot really survive or can't claim that level of average tensile strength only if they have a 20 defects less than 20 nanometers over thousands of miles of carbon fiber. That's the strength limitation. And if you extrapolate that a little further, you can see that if we, for example, consider a defect that would be 1 nanometer, which is 1/100000th of 1 meter on the filament, those strengths would be predicted to be somewhere on the order of 20 gigapascal, which is in fact what Bacon observed in 1959. But doing that over long lengths, over long scales, is the real heart of the manufacturing challenge of carbon fiber to achieve high strength carbon fiber. Also, these pan-based carbon fibers are not particularly graphitic, the high-strength pan fibers. In fact, they're produced in this publication describes it, they're produced in this temperature range of 12 to 1400 degrees, whereas these highly graphitic fibers will see temperatures far over 1800, maybe even over 2500 degrees C. So you're left with a structure which is in this case described as a wavy graphene-like structure. You have more of an amorphous type structure in the carbon, albeit it's largely all oriented along the axis of the filament. There isn't long-range order as you would find in a highly crystalline graphitic fiber. And the constituent basal planes are wrapped into each other. And this was actually known in the 80s. I would like to point out, I guess, on the far right, one of these papers from the Oberlin group of France described after pretty laborious TEM studies, looking at the fibers, that as this sort of radius of curvature that they observed in the TM of these basal graphitic planes became tighter and tighter, the strengths went up. And one way I would explain this is let's step back. Have any of you guys ever split a piece of wood with, say, an axe? And if you have wood that has really oriented grain, it's far easier to split. But if you have, for example, wood that has some gnarled character to it, you're going to have to wrestle that to get it to split. So that somewhat analogously is going on in these carbon fiber structures. The issue is you need material that is resistant to the propagation of cracks, and in this case, very micro cracks, right? That's what gives you the high strength and the high strain to failure of these pan-based fibers compared to the very graphitic fibers like the mesophase pitch fiber. Okay, so I want to now, having discussed about history and properties of pan-based and other carbon fibers, turn your attention to what we do at my lab at the University of Kentucky. And we do research on pan-based carbon fibers. And to do that, we have to make our own pan precursor fibers. This is done through a solution spinning process. It kind of plays out from left to right on the screen. But I want to point this out. This means that unlike nylon or polypropylene or polyesters, which you can melt, right, and just sort of pump the molten polymer through a shower head of holes and draw that down to filaments, polyacrylonitrile doesn't do that. If you try to melt it, it's pretty akin to trying to like melt baking flour or something like that. You know, it just burns. It essentially pyrolyzes. You're not going to find yourself with a liquid. But after all, that's what you want, right? Because if you had thermoplastic meltable polymer fibers, when you went to carbonize those to produce carbon fiber, you melt them all together. That's not good. So solution spinning is the way that polyacrylonitrile fiber is produced. And it involves, at the beginning here, extruding the filaments through a shower head of holes through an air gap. This air gap is about 1 centimeter, and then we're accelerating those filaments down into a liquid bath. And the solvent diffuses into the liquid bath, which contains water. Water diffuses into the forming nascent filaments and essentially precipitates that into solid polyacrylonitrile. This then goes down the spin line to be washed and stretched. We stretch it in boiling water or really hot water, and then stretched again in hot glycerol to get the temperature up a little bit higher above the glass transition. And then we apply a spin finish, dry the fibers and take those up. So I do have some videos here that sort of describes that. Let's see if these are going to work. Good. So in this case, we'll have experimental polyacrylonitrile dope in this, our solution in this pump. We'll pump it through a filter and then over to the spin head with this sort of yellow insulating foam on it. The filaments form in the air gap and then are drawn down into this bath, forming. In this case, it's, I think, a 100 filament tow that's being formed and being taken up. When I say tow, that's just the unidirectional collimated bundle of the filaments. In industry, that would be more like 3,000, 12,000, 24,000. We're doing 100. After that, the tow makes its way down the line through water baths, which are there to essentially wash the fiber of any residual solvent that's trapped within the porosity of the nascent filaments. And then down when we get to the end here, we're going to do some higher temperature stretching, which is going to go kind of fast here. The fibers are drawn through hot water. We're essentially accelerating and attenuating the filaments. They're dried at this case, and then the dry filaments go into hot glycerol above the glass transition temperature. They're drawn again, and then you can see that the filament's smaller, maybe a little bit more lustrous. That filament goes through hot water to wash off any excess glycerol. We apply a spin finish, dry that, and then the filament's taken up. It's a really fast video, everybody, but that's essentially how industry produces pan-based carbon fiber. We rather mimic that in our lab so we can get away with small quantities, yet produce enough to do some meaningful research on. Now, those fibers will be converted to carbon thermally. As I mentioned, back to 1950, you certainly observe this color transition from white to yellow to brown to black as we go through chemical transitions associated with the cyclization of the nitrile group on the polyacrylonitrile, forming these intermediate cyclic structure here, which has some measure of oxygen functionalities on it. That's what we call the stabilized polyacrylonitrile, which is ready then to be subjected to the high temperatures of carbonization, which is done usually between 500 and 1500 C for most of our standard and intermediate modulus grade carbon fibers, and some heat treated above 2200 to form higher modulus carbon fibers. This is a sort of layout how this mechanically works from left to right. There's a really nice YouTube video on this if you want to take a look. It's by SGL BMW, so I've credited them here because I ripped off these pictures. But I want to point out that the oxidation process is by far the bottleneck of producing carbon fiber. These are huge oxidation ovens, and the fibers going through this in a serpentine fashion, kind of through each of these, with residence times on the order of about 100 minutes. However, on the carbonization side, we have what we call our low temp and high temp carbonizations. Those processes will happen on the order of about 100 seconds. So the oxidation side of producing pan-based carbon fiber is slow, really slow. When you go look at these, you can see the bobbins really, or the cores turning just really slow rates. Relative, if you went to a textile plant, it would be zipping along producing fiber really fast. In fact, the precursor fiber spinning back here is, relatively fast to this. So carbon fiber production is slow. This is partly why carbon fibers are expensive. We need to figure out ways to do this faster, perhaps. Let's come back to that. So I'll talk about some of the research we're now doing at my labs in this area. We're looking at making hollow pan-based carbon fibers. So you can see on the upper right, those are some of our hollow carbon fibers that we produced from pan. Why? Well, we're interested in always increasing specific properties, and a hollow fiber, for all intents and purposes, has lower density. After all, the composite matrix doesn't know the fiber's hollow. There are other reasons too. Chief of which is we have the prospect of achieving stabilization much faster in a hollow filament relative to a solid one, and lower cost because we could produce them faster and so forth. We're also producing pitch-based carbon fibers from coal. or particularly from coal extract. This is of interest, generally speaking, from the point of view of coal utilization, but there is also quite a lot of pressure on coal tar and less of that stuff around, which is used for a host of applications in the metallurgical business. So we'll talk about those two things. So back to the hollow fiber. Why would we be looking at hollow? Well, it turns out some of these intermediate modulus carbon fibers, like Torres T700, has a structure of a skin and a core, right? Turns out that skin is far more oriented, has higher modulus, and can essentially handle more load than the core. And this structure, we believe, is sort of an aftermath of insufficient oxidation. Even in the optical microscope, you can see the skin core structure of the oxidized pan-based carbon fiber. And we took some of Torres T700, chopped it into bits and put it into a TGA, heated that up to 600 degrees over a couple hours. And you can see that it essentially selectively burns out the less oriented carbon, leaving these sort of pits on the ends of the cut filaments. So we've proposed to essentially spin a hollow fiber and sort of make more efficient use of the carbon that is there, if at all possible, on the basis of the mass of the fiber, so the density. So our goal is to essentially produce the fiber shown in yellow. This is funded by the Department of Energy right now. And then the other primary reason is the prospect for faster oxidation of the hollow filaments. So we took some data. Well, let me describe what this chart is telling us. One of the questions we always ask ourselves is when we're oxidizing pan fiber is, when are the cookies done? How do you know that you've arrived at the proper oxidation state? And we follow that with the density of the filaments, which we measure by a density gradient column. 1.35 grams per cc is an ideal oxidized density. The starting pan fiber is around 1.18 grams per cc. When you take a really large diameter fiber, the number of minutes at 250 degrees C to arrive at a density of 1.35 is high. So that's the point up here. As we make smaller and smaller filaments, the number of minutes at 250 to arrive at the density marches downward. And in this case, the kind of diameters associated with the production of current pan-based carbon fibers point something on the order of 66 minutes at 250 C to arrive at that density. We predict with our targeted hollow fiber, we would arrive there in 30 minutes. So cut that time in half. That's one of the things that we're really trying to do. Now, we haven't yet done it, and why? Well, it turns out spinning these hollow fibers is hard. Nature wants to collapse these tiny filaments as we go smaller and smaller and smaller. So my group has been really focused on trying to produce ever smaller hollow fiber precursors, and I'll show you some of those, so that we can really scientifically test this hypothesis. We're spinning them with shaped spinneret technology. We essentially spin a left and a right side of the fiber, which when it passes through that air gap, those two sides come together and heal. And as they heal, they create this sort of pocket at the top, which is pulling air into the inside of the fibers, almost as if it's continuously blowing a bubble, but it's preventing a vacuum from the filaments from collapsing. And that's like, for example, the length of the air gap is a big player in that. This is an actual image of a hollow fiber being formed, and you can see the two walls in that sort of microscopic image. This is just a perspective image on a bundle of hollow fibers that we pull out of that bath right at the very beginning before we've stretched them. And that's the tip of a ballpoint pen, just to give you a little bit of perspective on the fibers before they're stretched. And then these are the filaments look like. On the far left, on the spool, you can't tell any difference. They just look like solid filaments. But under the, in this case, SEM image, you can see all the filaments are hollow. Sorry about that. All the filaments are hollow, and a little bit closer, you've got these circular hollow filaments. And We published on this back in 2021, and we've made a lot of progress since then. But one of the things that we are interested about this technique is it should be able to be dropped in at existing pan production plants. That is the shape spinneret technology and the processing to produce these fibers. Good.
Are the manufacturers working on the same technology?
I know that manufacturers have worked on this technology. No one in the commercial sector is broadcasting that. However, there is one patent of interest in this area that of all places came from the Hyundai Motor Corporation.
Mhm.
Yeah. So anyway, it is my opinion that folks have looked at producing hollow fibers and some of the challenges in making them ever smaller to be relevant to produce carbon fiber have sort of deterred some further advancement in the area. So we're working on that. Interesting on the fibers, the hollow fibers that we have been able to produce. In the upper right, you'll see this is an optical microscope image of the fracture surface, just looking straight down one of these hollow fibers. You'll see that there's this bright band around the exterior of the filament. It's almost a pretty clear front in between them, and then this darker material inside. We posit that that is on the outside well oxidized material, which is reflecting more photons because of its conjugated bonding compared to the material on the inside. So we put this kind of to the test with Raman spectroscopy, which we mapped spatially on top of fibers that had been treated to increasing temperatures. So if we look at 180 degrees C, we're mapping the ID to IG ratio in the Raman right on top of spatially of the filament. And what you need to know is that as this ID to IG ratio goes down, we're going to be seeing more conjugated bonding associated with graphitic material. So as it goes from red to green to blue to black, it becomes more conjugated. So we've got really aliphatic material after only 180 degrees. We go to 230 and we start to see now in the Raman, spatially right on top of the fiber, this area of increased conjugated bonding. Going over to 260, it progresses, and after 280, it's progressed even more. But you still see quite a bit of red on the interior of these filaments, as you did at the very beginning. It's as if there is a limit to the size of the filament that is accessible for oxidation. This explains why carbon fibers are tiny in diameter. And it suggests, though, that we could, in fact, well oxidize a hollow fiber if and only we could produce it small enough, which is what we're working on. Good. So yeah, it's these aliphatic hydrogens up here, this aliphatic bonding up here that I've circled in red, as opposed to the conjugated bonding after the material is dehydrogenated in the presence of oxygen, is what we believe is underpinning these results. It's as if the oxidized layer is a barrier for oxygen to go through, which is, we see this in all kinds of materials, right? Cut an apple, look at an avocado or a piece of steel or aluminum, everything has these oxide layers. Okay, we have, with our partners at Oak Ridge, been able to take continuous tows of the hollow filaments and convert those into carbon fiber continuously, this is an experimental result of that. And if we look in the SEM, this is the same ballpoint pen with these hollow carbon fibers, down to about 15 micron on the diameter. We still need to get that smaller. If we look at the effective modulus that we have measured, we're landing around 196 gigapascal with our 18 micron outer diameter hollow carbon fiber. Now, when we calculate that, we're using this effective diameter. That means in the cross-sectional area, we're including the hole, which is fair because the composite doesn't know there's a hole there. So you have to do that. That brings our numbers down. But these results do trend to us that we'd arrive at 230 if we could produce a fiber that was 12 micron OD. That's where we're going. But the big point is that the effective density is now down at about 1.23 relative to about 1.8 That's a big drop in density, which I think I really can't underscore more, because if you weren't concerned about density, one could argue that you would just use glass fiber, just make a thicker part, spend a lot less money than to spend the extra money to go for a carbon fiber part. It's all about lower weight in the part. Now, switching gears to our mesophase pitch-based carbon fibers from coal. We are funded by the Department of Energy to develop this. I describe this as a wide river. We're trying to bridge it. On one bank, we have our coal, and on the other, we have our final carbon fiber. We are converting coal to liquid through a direct coal liquefaction process. Once we have the coal extract liquid, we dilute that in a solvent and filter it, and then we recover that solvent. And then we thermally convert that filtered coal liquid over into mesophase pitch on the far right, it's depicted, which can be melted and then spun into fiber, which can be oxidized, carbonized, and graphitized to produce really high modulus fiber. But let's remember, it's interesting because it is true that pitch can be melt spun and carbonized. But why doesn't it all melt back together when you heat it? Well, pitch goes through oxidation reactions as well, and those take time as well. So that's another issue going on with pitch-based fiber. One application for these could be in the area of, for lack of a better term, containers, lightweight containers for automotive electric EV batteries. EV vehicles are interesting, right? But no matter how you look at it, the batteries have very low energy density compared to hydrocarbon fuels, which means you must have a big battery for your car, which means it weighs a lot. In fact, electric vehicles are heavy, even relative to their internal combustion counterparts. So lightweighting other parts of the vehicle through perhaps carbon fiber composites is of interest. We published a paper on having achieved a high performance carbon fiber from coal extract back in May. And I want to kind of get at the takeaway of that. Bottom line, when we used our coal extract relative to our petroleum decant oil, which is the sort of baseline for the study, we were able to produce 86% more mesophase pitch than we otherwise would have. That's a win. And at the end of the day, we produced 69% more mass, more carbon fiber than we otherwise would have. So that suggested that we could rationally utilize these coal extracts for the production of carbon fiber. But we took a hit. We took a hit in the modulus. So the petroleum decant oil modulus at 795, which is incredibly high. Remember, pan-based carbon fibers have moduli that are typically around 250 on kind of the high end. So this is 795. And with our coal extract, we were about 475. But we were able to produce almost 70% more than we otherwise would. So there's that value. We were able to show as well that this is pinned to the crystal structure. So these L sub C is the cohesive length of the graphite crystals in the C direction. At 286 for our decant oil or our baseline fiber, marched down to about 215 for our coal extract derived fiber, which explains the lower modulus. But we're making progress in this area as well. So as I finish up here, a couple things I'd like to bring up. What are some other carbon fibers and what's next? But let's talk a little bit about the global size of carbon fiber market. So I'm not going to go into huge specifics here, but I'm going to say it's around 150,000 tons of carbon fiber that are produced each year globally. That might sound like a lot, but if we look, for example, at glass fiber, something like 5 million metric tons of glass fibers produced each year at a price of somewhere around $3 to $4 a pound. That's about an order of magnitude cheaper than carbon fiber, and carbon fibers just there's far less of that out there. But remember, glass fiber can be spun, melt spun, just really fast relative to carbon fiber. So it is my opinion that we need to manufacture carbon fiber more efficiently than we're currently doing, with less, quote, steps to get there. Perhaps more like glass fiber. And, I hope I've made an argument that the current process is a little bit slow and complicated. That said, what's going on currently is a scale-up type process. So these are processed in continuous tows of fiber. They call the small tow. These are the small tow. Sorry, the upper one is the regular tow. Let's say they described it here. If we increase to what's called a large tow, which might comprise filaments of maybe 50,000 or more filaments per each tow, you can make more carbon fiber per unit time, which can drive its cost down. But you take a hit in tensile strength and you start processing more and more fibers at the same time, which limits some of its application. So that's what's going on currently in the industry. There are, though, interesting glimpses of future. This is actually going back up, this case to 91, but there are before that. These are directly carbonizable polymer, and you can make fibers from these. These are kind of like Kevlar fibers. These are polyaromatic or the polyaramid type fibers. PBO is polyparaphenylene benzo bisoxazine over here. Sorry about that. We can spin fibers from this, which we can convert to carbon without doing oxidation at all. You just basically convert them, heat them to carbon, and you're done. Cut out that hundreds of minutes of oxidation. Same with the PBZT, which is the sulfonated version of PBO. So this is interesting, but it turns out the cost of these precursor fibers is so high that it makes more economic sense to make carbon fiber slowly from polyacrylonitrile still. Bio-derived fibers. So you guys you may recall I talked about the very first carbon fibers were produced from cellulose. The other half of the tree is essentially lignin. And all of the paper processing plants make lots of lignin, which is used as a fuel in production of paper. But lignin garnered a lot of attention over the last, I would say, 20 years, potentially for carbon fiber precursor. And I'm just highlighting one of these papers that came out rather recently. And this is the first one that I've ever seen describe high strength and high modulus from a lignin-derived fiber. They talk about this stemming from applying tension, much like what was done with PAN back in the early 60s. But these lignin fibers are incredibly brittle. So applying that tension has to be done very carefully. Also, baked into that paper is an oxidation or a stabilization process that was tens of hours long. So there's a little bit of a downer on that. But again, it is a abundant available biopolymer that can be produced to carbon fiber. So there could be ways to arrive there much faster and much more efficiently, which would be great.
Who's doing that work?
This was out of Iowa State, Yixin Luo.
Yeah, it's in the US.
Yeah. Then lastly, I want to talk briefly about the carbon nanotube yarns. And I'm going to, from my perspective, or from a perspective, these offer lower steps altogether because there is no oxidation and there is no carbonization. You essentially spin fibers from the carbon nanotubes and you're done, which is attractive. Of course, the nanotubes are not abundant and they're not cheap. There's that, right? For now. But the Pasquale group at Rice University has pioneered a lot of this. They're spinning this. This was licensed by the Teijin Japanese Fiber Corporation to spin nanotube yarns from superacids, much like Kevlar fiber is produced. Yeah, which is, I think, why Teijin was interested in it. The resultant properties are pretty remarkable. If you check out the red stars, really high modulus, really high strength. Definitely competing property-wise with existing state-of-the-art carbon fibers. Again, no oxidation, no carbonization. Pretty attractive. So we'll see where this technology goes. And lastly, I want to talk about what I think there's a need for, what I call lower embodied energy carbon fiber. Producing carbon fiber is energy intensive. So this particular study called out 966 megajoules per kilogram of carbon fiber composite, 704 of which stemmed from just producing the carbon fiber alone. Let's compare that to steel. Producing steel is 33 megajoules per kilogram. Not to mention, steel is far simpler to recycle, right? This is why I think there is a bit of a stepping back from producing passenger vehicles with carbon fiber. If the product, if in this case the car doesn't have a really long lifetime, then you're not likely to get your return on your initial investment to having produced the carbon fiber to begin with. And we studied this briefly by plotting here. Let's look at the right orange axis. The miles per gallon of a vehicle, this is based on DOE data that we put together, as we replaced steel with carbon fiber. So this on the x-axis is the number of kilograms of steel that we replace. You can see that the miles per gallon goes up from something like 25 to 40 miles per gallon as we replace lots and lots of the steel with carbon fiber composite, which you would expect. Problem is that the number of miles you have to drive that vehicle to break even energetically for that investment in carbon fiber marches up lockstep with it, right? So, right now, replacing something like 100 kilos of steel in an average passenger vehicle, you're going to have to drive that vehicle something around 80,000 miles to essentially pay back the energy penalty it took to produce the carbon fiber relative to steel. Now, if you got an aircraft that's flying 50 years, 11 hours a day, it can save so much fuel that this initial payment and this initial payback periods, you get there far beyond. But with vehicles, passenger cars and so on, I think this is something that's limiting the uptake of carbon fiber. So we need to figure out how to make lower embodied energy.
That was aluminum. How would aluminum fit into this?
I don't know.
Isn't that the primary?
High strength aluminum is sort of in the middle now.
Is it?
Yeah.
Yeah.
Ford's got all high strength aluminum bodies and chassis.
Yeah.
Because of that.
Yeah. Aluminum requires quite a bit of energy to produce as well.
Yeah.
Yeah.
I don't know what that means.
Yeah.
It's nowhere near that high.
But it's not that high. And these numbers are arguable,
Yeah.
right? I mean, that's not a material
Yeah.
property. That's someone putting together,
Yeah.
summing the energy, what they know and so forth.
Yeah.
But yeah, aluminum is pretty energy intensive as well, but I agree it's not that high. Yeah.
So if you look at recycled fibers in the same perspective,
Mhm.
I guess it'd be even theoretically even more expensive to make because you're producing the fiber, you put it in the composite, you're using more energy to burn that composite off.
Yeah. Recycling.
Depends on the method though.
Yeah.
There are
Recycling.
non-stable methods.
Yeah. I would also point out too that when BMW and SGL went to the joint venture to produce these i-vehicles, the i3 and the i8 with lots of carbon fiber, they built a plant in Moses Lake, Washington. Why? Well, they got all of their power from a hydroelectric plant. So they write off a lot of this energy penalty because it's all green energy producing that fiber. Yeah. So there's a lot of aspects swirling around the energy argument, but nonetheless, production of carbon fiber is pretty complicated, slow, and requires a lot of energy.
When you look at the current state of carbon nanotube or nanofiber production, how energy intensive is that as compared to carbon fiber production?
I would say it's far lower. I don't have numbers to that, but I would say it's far lower energy. But the part about that causes me pause is I don't know what the yields are. It could be it could be relatively low yield, which would back that up currently. So I don't know.
We got a message from the audience from Matt McGinnis, 190 to 230 megajoules of primary energy per kilogram. For
Love that, dude.
Okay.
That's
There you go.
it's like a third.
Yeah.
right?
Thanks, Matt.
All right. So just to wrap up,
Let him finish, guys.
Yeah, just to wrap up, we've reviewed some applications of carbon fiber, the history of carbon fiber. Thanks for going on that journey with me. And landed at the dominance of the pan-based carbon fiber, these tough, resilient carbon fibers compared to the pitch-based carbon fibers, which are far more brittle. We talked here about the shortcomings of carbon fiber. It's complex, slow processing, high cost, high energy. And then future carbon fibers, what's going on is increasing the volume, lower cost precursors, prospect of one-step precursors, and like we're working on these hollow precursors. I also want to end on plugging the Carbon Conference. The World Carbon Conference will be in Saint-Malo, France, at the end of June into the beginning of July this year. And it's going to cover these 11 broad topics. You can take a look at their website. And I guess my plug down here for postdocs, I was given that at a lot of other universities. But look, guys, thank you very much for your attention. Appreciate it.